Okay, everyone, welcome back to CSE 373. This week, we're going to be talking about a really new and cool type of data structure called a graph. I'll kind of mention this again in a bit, but this idea of a graph that we're going to introduce is not quite an ADT or a particular data structure. It's kind of a broad set of data structures. It's kind of a category of data structures that solve really interesting real-world problems. So we're going to see graphs pop up all the time, not just in computing applications, but in a lot of real-life applications. And understanding how to represent a problem using this thing called a graph is kind of like a computer science superpower. Because once you're able to model something with a graph, you have this whole set of algorithms and terminology to use on it to solve really interesting real world problems by mapping it to this kind of abstract notion that we're going to talk about today. So we're going to be talking a lot about applications and trying to talk about, today at least, some of just the fundamental terminology for these things, so that we can set ourselves up for the next couple of weeks where we're talking about various algorithms that operate on these structures. So before I get into what graphs are and all that stuff, let's start with some announcements. So do remember, this is a recording for Monday's lecture, so the Project 2 late cutoff is as Monday night at 11:59 p.m. Do remember that if you're watching this on Monday, it's after Sunday, November 1st, we have changed time zones. So just make sure that you know what time 11:59 p.m. is in Seattle. We also released P3 last week when P2 was due. It's due just under, that's supposed to say 2 weeks. I'll fix that on the slides. It's due on Friday at 11:13. Please try to start this one early. It's a 2-week project because it can be a little tough. As I mentioned in my email to the class last week, talking about kind of the mid-quarter feedback, one of the things we were trying to be a little bit more conscientious of is tying our lecture material to the assessments that you're doing in this course. So you're going to find lecture 12 and 13 about heaps very, very useful in terms of implementing the heap in part 3. Now, do remember, as I highlighted at the end of lecture 13, that the heap that you're implementing in P3, while it's going to be very, very similar to the structure that we talked about in class, and you should definitely use that as a starting point, we have those extra operations, change priority and contains, which are not going to be efficient on that implementation of the heap that we described. So we're going to tell you that you're going to want to use an extra data structure in your problem to help you answer this change priority and contains problem. We recommend ignore this extra data structure at first. Just get it working. You'll probably fail the efficiency tests. And then once you have kind of a working version, see what parts can I maybe make more efficient by using another data structure. So we just wanted to give you a heads up that that part is going to look different than what we talked about in lecture, but we're trying to give you lots of advice for how to tackle those problems. We also will have a new exercise out at the end of this week. Exercise 3 is going to be focusing on the post-exam content so far, primarily focusing on the stuff we're talking about this week, this thing called BFS, DFS, and Dijkstra's algorithms. But we'll introduce those later, so don't worry if you haven't heard those terms quite yet. So on to today's learning objectives. We kind of have 4 big objectives for today. We want you to be able to categorize graph data structures based off properties they'll exhibit. So we're going to talk about a lot of different properties these graphs can have, lots of variations, which is part of the reason why they're so flexible. We want you to be able to select which properties of a graph would be most appropriate to model a scenario. So we'll outline a lot of properties, and we wanted to say, okay, if I have this scenario like the subway map of Paris, what type of graph will I want to use to model that? Then we want you to be able to compare the runtimes of these different graph implementations, the adjacency matrix and the adjacency list, and select the most appropriate one for a particular problem. And then we're going to introduce the high-level algorithm for this ST connectivity problem, and we want you to be able to expand on that going forward. So really understanding that kind of core basis and how it will expand on that kind of going on into our algorithms for the next week. So in this video, I want to introduce kind of some definitions of what graphs are and kind of talk about where they show up, because I've been using this word graph quite a bit and I haven't told you what that is. Before I can describe a graph, I have one more last thing, which is I want to do a little bit of review of trees. So as a reminder, we've been talking about binary trees for a while. A tree is just a collection of nodes where each node has at most one parent and at least 0 children. Now, most commonly, we've talked about binary trees, where each node has at most 2 children, but tree is a very generic concept, and we talked about root nodes and leaf nodes and subtrees, but we've been kind of familiar with this idea of a tree for a while. Now, one of the reasons I wanted to bring up trees in particular is a tree, in some sense, is kind of a category of data structures. We saw lots of different types of data structures that act in this tree-like way. We had binary search trees and AVL trees. We also saw these kind of weird B plus trees where they had this internal node and the leaf node with all the actual data. And then we introduced these binary min heaps. These are all types of trees. They're all different data structures, but I wouldn't quite call like a tree an ADT, an abstract data type. It's more of a description of a bunch of different data structures kind of act like this. And this is kind of going to get us at kind of this idea that this graph thing I'm going to introduce is not necessarily a particular data structure, but a type of data structure that lots of different implementations might try to behave like that, just like how we have many different implementations of the idea of a tree. Now, one of the things that when we talk about data structures like lists or maps or anything is they're storing data. Now, one thing that's usually sometimes useful to model in your data is relationships between the data. So I have 2 elements. What's the relationship between them? Are they friends? Are they enemies? What are they? So we sometimes like to think about interdata relationships. So if you think back to some of the data structures we've talked about, so if you think to something like an array, arrays don't do a very good job at trying to capture any interdata relationships. The elements of an array just store the data itself. It doesn't really store any connection about how index 1 relates to index 6. Really, the only connection we have with the data is the order. So sometimes we might say that like the index 0 is the like best thing, and then index 1 is the next best thing, but all you really get is some kind of global property usually. You don't really get this kind of like, how does A relate to C? When we introduce another type of data structure like a tree, we started kind of encoding this notion of relationships. So the elements of our data structure stored relationships to other elements. So in the tree example, we usually stored some kind of hierarchy where there's a node at the top and it had children that were these other nodes. But the important thing there is that the way we represent the data in the tree allows for us to define these relationships. We'll define how one element is related to another, in some sense by its child or parent relationship. Now, trees have a very strict structure that I mentioned, where each node has at most one parent and at most n children, or not n, but k children, where you're talking about a k-ary tree, so binary tree at most 2 children, but there's this very kind of strict structure there. And so when I'm going to be introducing this idea of a graph, it's really an extension of that idea of a tree. It's really about encoding this interdata relationships, but kind of removing a lot of the strict structure that trees have. So a graph is, in some sense, a way of having elements and the connections store relationships about the data. And the relationship dictates the structure. There is a huge freedom that you can get with these connections. So if you think of a tree like a family tree or a hierarchy, a graph is more like a social network where all of the nodes are in some sense equal and they can have relationships or friendships between each other. We call these edges, and they can kind of form these vast, beautiful structures. But there's not necessarily always a bunch of strict rules that say what things are allowed to be graphs, what things aren't. We kind of just let the relationships go, and we can and try to use properties of those relationships to make statements about the data or run algorithms on them. So a graph is in some sense a very, very loose type of tree. In fact, we usually talk about trees as actually being a special case of graphs. It's just a graph with a very particular structure, where each node has at most one parent and it has at most 2 children or whatever type of tree you're in. A graph kind of lets friendships go in any way, shape, or form. So why to introduce this general notion of a graph? Well, it's because basically everything is a graph. Most things we've studied this quarter can be framed in these graph terms, where you have data that's related to other pieces of data. So for example, anything that we've talked about trees so far, I just mentioned a tree is a special type of a graph. This is a graph with a very particular structure. Linked lists, hey, they're also graphs. They're graphs where everything kind of goes in one direction. Heaps, because that's a tree, also a graph. Now, it's not just things that we've talked about this quarter, but most applications you can think of involve graphs somehow. If you think about Google Maps has some kind of notion of locations like buildings, and it has kind of information about paths from one building to another. You can imagine having representing this as a graph where the nodes on like the circles in that structure are the places, like the building, like the Allen School building or your favorite restaurant on the Ave. And the edges, the things connecting them, the relationships, are like paths from one place to another, or like roads to get there. Facebook, that's an actual social network. You can imagine the nodes in the graph being people, and those relationships being friendships. They even have, if you ever like kind of look into a lot of the Facebook documentation, they have this thing called a graph search. It's because they back their entire social network with this graph structure. You've been using GitLab to commit things. Your commits form a graph where one commit has parents and they can actually have multiple parents in some sense. There's this nice graphical structure to them. Pretty much anything you can think of, you could probably model as a graph somehow. This is what makes them so powerful, is because they're so generic and they're so ubiquitous. Now, there are so many specific applications we can get into with graphs. There is no way I can list them all. But I do think it's useful to go through some and kind of highlight some properties about them so we could see kind of how vast this idea that we're going to be talking about is. So lots of times graphs show up when you talk about things like physical maps. I mentioned Google Maps, but if you're thinking about traveling from one place to another, like an airline map, the nodes, or what we sometimes call vertices, are airports. And the edges, the things connecting vertices, are flight paths. So you could take a flight from LA to New York or something like that. And you could maybe imagine trying to represent all the flights that are happening at the US at any point in time or across the world. If you're thinking about traffic, you could think about the intersections as nodes in the graph and kind of the edges as being roads between them, and trying to find bottlenecks in your traffic in your city when maybe at different times in the day there is a lot more traffic that cause traffic jams. Anytime you're trying to model relationships, graphs are really great structures to reach for. So anytime you're thinking about social networks or social media, all of these things are modeled in graph structure. Who's friends with who is maybe an influencer, maybe one person that has a lot of people following them. Lots of interesting things you can ask there. And even code bases, thinking about how projects relate to one another. One of the things you've been using graphs this whole quarter, every time you run your project, you use Gradle, which is a build system. And Gradle uses a graph to write out the dependencies of the project and recompile things based off what's changing. So it doesn't have to recompile the whole project from scratch each time. If you think about biological applications, graphs show up all of the time because a huge part of biology is trying to figure out what things affect biological systems. Like, for example, what types of effects will influence cancer outcomes, either causing cancer or curing cancer. All of these things are modeled by a lot of times they're modeled by graphical structures, where maybe we assume that there's a graph going on behind the scenes of nodes acting as some biological system, and I'm not a biologist, I have no idea how anything in the body works. But these nodes are some kind of biological system. The edges, the relationship between them, are kind of how one thing affects another. And then they're trying to learn what this graph is by doing experiments, gathering data. They're trying to figure out what is the underlying graph that dictates how the physical world works. And it even applies all the time in just computer science topics. So when we think about web pages all the time are modeled in these graph structures where you have pages linking to other pages. This is how Google's search algorithm works. They call it PageRank. They use this graphical structure to try to find the pages that are really, really popular. And Wikipedia is the same, where it kind of links one page to another and you get these nice network effects. So graphs, I hope by now I've convinced you, show up everywhere. There is no limitation to what we can represent with graphs. They show up all the time. Now, I should say, there definitely are things that you can't model with graphs, but graphs show up all the time whenever you're talking about relationships. However, one piece of data relates to another, that's usually a case that you want to be talking about graphs. And relationships show up all of the time in physical applications. So I've mentioned all these applications. Let's talk about what is a graph. So I'm going to start with one definition here. And then in our next video, I'm going to bring up a bunch of terms and properties that are important to know, but we'll get used to them over time. But at its simplest, a graph is actually just two sets. It's a set of vertices that we usually label as V, and a set of edges that we label as E. Commonly, we also call these vertices nodes. We use that term interchangeably. But any graph is described by what vertices are in it and what edges are in it. So each vertex is a node. It just has like one piece of data, like A, B, C, D, or whatever. And then the edge is a pair of vertices, where it says this is one. An edge always connects two vertices. Vertex. Vertices. That's the right word. I always mix up vertex and vertices. It connects two vertices or two nodes, and it says like this node is connected to this node. Now we also, just a bit of notation, we usually use this kind of vertical bar notation to talk about the magnitude of a set or the cardinality of that set. What that really means is just the size. So when I say vertical bar V, vertical bar, what I'm saying is the number of vertices. And the same thing with E is the number of edges. And we sometimes use the variables N for the number of vertices or the number of nodes, and M for edges. Pretend there's an M somewhere in. So this is a graph. It's this linked structure where nodes relate to other nodes via edges. And we define it in terms of these two sets, the set of nodes and the set of edges. And that gives you any definition of a graph. Now, I'm going to stop this video here. In our next video, we'll talk about lots of different other properties we might imagine a graph having, and we'll talk through terms that define those properties.